All right, it is time the recorder should have started automatically. See how well synchronized it is. All right. So I'm gonna get started with this one first. This is from NPR. Whether you guys agree with what NPR has to say or not is not really the core issue here, because they pull these content from somewhere else. Okay, it's just a reporting. So here is the. Let me zoom in a little bit here. Oh, it won't zoom. It does a little bit. Okay. So for those of you who cannot read, because we are not interested in this part of the chart, only this part, right? So the top paying major is the first one is petroleum engineering. Not really surprising there, right? I think petroleum engineering is basically about how do you create products, okay, other chemicals and whatnot using petroleum. But I got bad news for people who are just getting into that field, because we are already post-peak in terms of oil production. What that means is, we can put in more effort to drill, to pump more oil, but it's not going to get us any more, okay? Because we are already past peak production in terms of extracting all the existing oil from underneath. Okay, so it can only dwindle. Maybe that's also another thing that they can work on, is to have synthetic petroleum or something like that. The second one is pharmacy sciences and administration. That's also very well paid. The third one, guess what, is mathematics and computer science. So there you go. You may not have made the best choice in terms of the highest earning, but it's not a bad choice either. Okay, unless you all want to be pharmacists and petroleum engineers. So, any feedback, any comments? Nothing?
You made the right choice.
Well, I don't think it's a bad choice, especially when this is something that you enjoy doing. That really is the key. I think computer science can be torturing to people who do not like to do programming, math, or logic. To those people, writing programs or dealing with computer science classes can be just pure torture, right? I mean, it's just nothing can be worse than that. It would be like me taking an art class and they talk about how this color goes with that color and this shape is nice, and I look at it and it's all the same. What is the difference here? I can tell you the RGB value and that's about it. So it's the same thing here. Or I go to a music class and my focus would be, what is the waveform of a violin playing? A $10,000 violin versus a $50 violin. What would be the spectrum difference? Well, you have more peaks over here and more overtone over there, and so on. But I have no appreciation of the actual music coming out of the violins.
I did a search on CNBC, something like this for computer science, and they had people who are getting into big data. They said that they start at like 120.
It's not uncommon. Okay, if you go to the Bay Area, I know a guy who is just graduating from Berkeley, from graduate school, and he got an offer from both Facebook and Google, and he has to choose between the two, and they were offering really top dollars for a graduate from UC Berkeley. Yep. So anyway, I just want to let you know, about this, these findings here. The other engineering fields are not bad, and I really think that computer science should be combined with something else. I mean, if you want to be competitive in in your career, it's really good to have a double major or a minor in something. I personally like mechanical engineering because it really lends itself to robotics, and that's really where things are heading. Everything is heading in that direction. All right. So any questions about this chart? No. Okay. And then all the way down here is counseling, psychology, and early childhood education, which is really unfortunate because those jobs are every bit as important as computer science. And unfortunately, it's just not well paid. All right, so I'm going to put this out of the way, and we have Scratch over here. The reason why I brought up this page is because at this point, I think some of us, are feeling, well, it's kind of boring to trace programs. I know how the programs, how they're supposed to work, and I want to actually test it out. I want to run the program on the computer and let it do something. This is really a quick and easy interface to write the programs. So what we'll do today is we'll finish up the pseudocode for factoring, and then we'll plug it into here and see whether we can make the cat, which is Scratch. The mascot is called Scratch, which is the cat. And we'll see whether we can get the program to work here with Scratch. Right. Before we go any further, we need to, you know what, I forgot one thing. I forgot to upload the test so I can talk about it. Did I actually forget? Yes, I did. I did it to the other class, but I forgot to upload it to this class. Let me see. I can get to it. And let's see if I can do this. Because I put everything on to my Google document, so I can actually get my documents from there too. All right, I have to sign up from the accounts, sign in to this one. All right. C, fall, P300, PM, exam 1. And these are all subfolders. I made photocopies of all your tests, so this way I can grade it just by logging into my Google Drive. I don't need to carry a big pile of paper with me. All right, so here's my file. We'll download it. What's that? Right click. Where's download? Download. Okay. Reviewing the test is also known as rubbing salt on wound. But it is a necessary process, because it is really important that we understand why points were deducted. So that way, in the final or even in exam 2, you know what to expect and also what to do and what not to do. If I don't go through this session, then some people can make the same mistake repeatedly, and then points will be deducted again. So it's really a good thing to kind of go over the test right after it. Okay, so this is our first question. We'll go over the answer first, and then we'll talk about the grading criteria. All right. So the way I do this is I'm just going to copy and paste this into an actual spreadsheet. Then we'll work with the actual spreadsheet here. All right. Let's resize everything a little bit. Here we go. Okay, so we have the algorithm, and then we go back to the test because it depends on your student ID. In this case, this particular student ID has a 6 as the third digit, and therefore the first set of values should be picked. So it's 9, 9, and 3 in this case. And let me go back to my spreadsheet, and we'll fill in these as 9, 9, and 3. Okay, so that part is really just part of the instruction here. It is important that we are starting on line 10 already, not pre. Okay, I hope nobody started with pre and went through the whole process. Okay, what do we do after line 10? The next line is line 2. Okay, very good. Okay, so we go back to line 2 because that's the beginning of the pre-checking loop. we re-evaluate the condition x is less than 10 is true. Then we go into line 3 because that's the body of the loop, which is a conditional statement. The first statement in the loop is a conditional statement, a multi-branch one. Okay, x equals a is false, 8 equals 9 is false. Okay, we move on to line 5 because it's a multi-branch. If the first branch is false, we keep moving on. So on line 5, we compare x to b. B has a value of 9 as well, so if the first one fails, the second one is going to fail as well. Then we move on to line 7 because as long as these conditions are false, we keep moving on until there's nothing left or there's an else. Okay? So this time we compare it to C. C has a value of 3. 8 equals 3 is also false. And now we have no choices left. Okay? Now since I did not have an else branch here, that means there's nothing else to do. What do we do next? Which line do we go to?
Line 10.
Line 10. Okay. So most of you remember now. There's a statement after the conditional statement, which is on line 10. So line 10 doesn't do much. It's just adding 1 to x. X goes from 8 to 9, and we already know that after line 10 we have to go back to line 2. So now we're back to line 2, and we evaluate the condition. Okay. It doesn't seem like anything exciting is happening here. Okay, x equals a is true this time because 9 equals 9 is true. Then we go to line 4. We execute the statement on line 4. Z gets a z plus 1. So we have z getting incremented to 11 here. And then what do we do? This is really the kind of more tricky part of this question. Where do we go after line 4? 10. We go straight to line 10. Okay, it's a multi-branch conditional statement. If one branch fires, or if we execute one branch, after that branch is finished, we exit the entire conditional statement. In this case, we continue execution on line 10. And on line 10, we increment x from 9 to 10. Then we go back to line 2. X is less than 10 is no longer true. It is false. Then we go to post, and it's done. Okay. So are there any questions about this question? Questions? All right. Let's move on. Moving on to the second question. The second question is also a trace. Okay, some people did not like this one too much because it has a repeat until loop. So we'll go ahead and take a look at this one first. And also we want to look at this ID is 9. So with 9 we start with 39, 41, and 5. 39, 41. 5. And because this is on line 4, the first thing we have to do is to fill in the comments part because we have a condition to evaluate. Okay? And I think I mentioned that in the instruction as well. Let me just double check. Add to the comments column if appropriate. And in this case, it is appropriate. All right, very good. All right. So the condition is x is greater than or equal to y. Is that true or false?
False.
It is false because x has a value of 39, y has a value of 41, so the condition is false. Then what do we do? Where do we go?
3.
We go back to line 3. It's a post-checking loop. If the condition is false, we have to go back and do the entire thing again. And it affects y. Y gets y minus k. So in this case, it's 41 minus 5, which will give us 36. We go back to line 4. Re-evaluate the condition. This time it is true because 39 is greater than or equal to 36. And then where do we go?
Post.
Go to post. Exactly. That's it. Because the loop on lines 2, 3, and 4 is the only statement in the then branch of the conditional statement. So once we are done with the only statement in the then branch, then we have to get out of the loop. And also out of the conditional statement. So that's why we go straight to post. There's nothing else to do in this case. Okay. Are there any questions? I saw some pictures. Oh, thank you. I saw some people drew pictures in the test, and I think most people who drew pictures actually got the answer correct because the picture really helped to show what should happen after the loop exits. Okay. So that's the second question. And moving on to the third question, which Many people told me it's confusing, but it's really, I thought it's really a lot of points so that people can actually pad the exam with the points, but apparently that is not the case. All right, so let's take a look at the code here, and then we'll try to figure out how to do it. Okay, let me just zoom in here so we can all read the instruction. Refer to the last 3 digits of your student ID and add them up. In our example, the sum is 13. Use that as the initial value of variable y. Okay, so y is a calculated value. Find an initial value of x to reach each possible branch and perform a full trace for each possible branch from start to finish. Okay, so this sentence is very important because it tells you what you're supposed to do with this question. Okay, the key word is each, not a. Okay, it makes a big difference. In each trace, fill in the pre-line with a calculated value of y and a value of x that you determine that will get to a particular assignment statement. You have potentially up to 5 traces because there are 5 branches. Lines 2, 4, 6, 8, and 10 are the branches. However, some branches may be dead, so you may not have all 5 branches. And just to make sure people don't come back to me and say, but you assigned 10 points to this thing, so I thought there are either 2 or 5 live branches. So I made this disclaimer here and say the score of this question does not necessarily indicate the number of reachable branches. Which is already a clue, right? I mean, saying, basically screaming, saying, maybe it's not 2 or 5, maybe it's something else. Okay. So are there any questions about the description, the instruction of the question itself? No? No one wants to accuse me for turning this class into an English reading class? No?
I still don't understand the question, but I'm sure you're going to break it down right now. So.
Yep, I'm going to do it. I'm actually going to answer my own question. Okay. All right, so let's go ahead and start on this one. I'm going to copy and paste the code first, and then we'll use 1 sheet per possible case in this case. So I'm going to start with sheet 2 as the first case, and just move things around a little bit until they fit. That. All right. So here we have sheet 2. We have comments because we do have conditions to evaluate. We have line number and the 2 variables that we have, and z, which is really doesn't do anything until the last moment. So they will look kind of like this. And I'll just format everything correctly. And there are 3 cases that we have to trace, so I'm going to pre-allocate everything from the beginning before I make any changes to sheet number 2. All right. So let's go ahead and get started here. Y is already predetermined. Z starts with an unknown value, and this is my precondition. X is also unknown. Well, X is something that you have to determine. Okay, so let me just take it back. All right. So the first thing you have to do is to determine which branch or which branches are possible. Okay. I don't know how you would go about doing it, but when I look at this particular code, I look at all the conditions first. The conditions are x is less than y, x is less than or equal to y, x equals y, x is greater than y, and x is greater than or equal to y. So they're all based on comparisons of just x and y. They're not really complex conditions. So one thing you can do is to say, how many ways can one value relate to another value? There are up to 3 ways, right? Less than, equal to, and greater than. So you can pick your value for x accordingly and see where it will take you. There cannot be 4 live branches. It's just not possible. Okay? There may be fewer, because if one of these branches is saying x is not the same as y, that will cover less than and greater than in one single, condition. So you may have only 2 live branches or even none, but there cannot be any more than 3. Okay, so does anyone want to suggest a particular value to try first?
12.
12. Okay, let's try 12. Okay, so once we have 12, we go to line 1. Line 1 has to evaluate the condition. X is less than y is true. Then where do we go? The condition is true. We go to line 2 because that's the branch corresponding to the condition. That is true. And that is going to assign the value of 1 to z. And then where do we go? Post, because we take one branch and then we just take off. I mean, there's nothing to do here. Okay, so that's one answer already. Okay, one of the 3. Let's move on to the second one. Okay, same thing here, 13, question mark. This is our precondition. Okay, can someone suggest another value for x?
13.
13 itself, okay, 13 itself, now is equal to. Okay, and we start with line 1, 2. Okay, remember every trace has to start from the beginning and trace through until we get to the end. That was also a part of the instruction. In fact, let me go back to the instruction here and see how redundant I was when I specified that. Okay, so we are talking about this one here. Okay, so let me just point out the important words here. Perform a full trace, not a partial trace, a full trace, and from start to finish. So I think that's kind of redundant because they're both implying that it has to be a trace from the beginning all the way to the end. All right, so getting back to the trace here. This is on line 1. Line 1 is evaluating the condition. X is less than y is false because 13 is not less than 13. Then where do we go? It's a multi-branch conditional statement. We go to line 3. Okay, so here it's line 3. X is less than or equal to y is true. Then we go to line 4. Z gets a value of 2. And then where do we go? Post. Get a post. Yep. So that's our second branch, second live branch here. And we are moving on to the last one. This is the precondition. Y has a calculated value of 13 in this case. Z has an unknown value. We have to determine another value for x so we can go to potentially a third live branch. We can try 14, okay? All right, so we start with line 1 again. X is less than y is false. Then we go to line 3. X is less than or equal to y is also false. Then we go to line 5. X equals y is false. Then we go to line 7. X is greater than y is true. So we go to line 8. As a result, Z gets a value of 4 in this case, and we're done. We get the post. Yep.
I got one problem, and that's that this is probably the easiest question out of all of them, but it was worded in a way that it was just kind of like, huh? And so it's just kind of frustrating because it's just like I'm looking at this, I'm just like, that's way simpler than all the other ones.
Well, especially when I do it. I get that a lot. It's like, heck, when you do it, it's so easy. I don't know. Well, maybe we can make this a learning experience for me. Go ahead and rewrite the question and send your sample to me. So that way I have a little sample to refer to. So next time I want to ask something like this, I can ask it in a slightly different way.
My biggest problem reading the question was that it was just one big block. I think if there had just been some spacing in there.
It's very
Some spacing.
Yeah, just to kind of break it up so you read a bit of information, and then you actually stop and you read the next one instead of just, okay, wait.
What did I just read?
What? Wait, reading again. Nope, not working. Wait, okay. Wait, nope.
How
still
about
kinda.
something like this? Let me just run this by you guys and see what you think of it. For each possible branch, do, and for. And before that, we have to do this first, okay? Compute y from your student ID. And then inside the loop here, we'll say for each possible branch, do the following, okay? Find a value of x to go to a branch that Yep, there you go. Okay. If there exists a value of x to get to this branch, then perform a full trace. How's that?
I'm quite all right with that. Yeah, I mean, heck, we're already doing it. You know, just get through the mind.
That's actually how a programmer would have done it, because that's the logic. Okay, for each branch, which means lines 2, 4, 6, 8, and 10, determine whether there's a value of x that can get you to that branch. If so, do a full trace. If not, do nothing and then go back and then go for the next branch.
All right. Yeah.
Would that fly?
Yeah.
It's a lot less wordy, for sure.
So if we submit an amended question, do we get like a couple points added to the test?
And of course, in an actual test, instead of saying there exists, spelling that out in English, I have to use the inverted E in mathematics. That's the there exists symbol, right? So anyway, I really tried my best to make it clear.
It
I
just
do not know how to.
through a couple times and just trying to process bits of it at a time, and not, like I said, not having that spacing at all. It was just kind of hard. It was just an information overload.
That's why we put indentations into programs.
And in paragraphs.
Yep. Alrighty. I'm sorry some of you find the instruction itself kind of difficult to understand. When you guys ask me the question, how do we do this one? I really tried my best to answer those questions, but I can't, I just don't know how to phrase it, in a way that is different from what I have already written. All right, so that's question number 3. I mean, it's really, that's number 3. And here's question number 4. I really, really like question number 4, and so do many of you, okay? Many of you actually wrote on the exam itself, and saying, this is cool, or, did you make a mistake? Is there a typo? No, there's no typo. It's a little gift. Okay, so let's go ahead and trace this one. This is our last one. All right, so here's the code, and we'll do the trace over here. Comments, line number. We have 2 variables, w and x here, and I'm just going to use the start value as written in the question itself. So the values would be 5 and 28, okay, for w and x. So 5 and 28 here, and this is the precondition, right? Yep, there you go. All right, so we can start the execution of the program. So we start with line 1. Okay, in this case, line 1 is asking x is less than, w is less than x is true. Then we move on to line 2, because line 2 is the then branch of this particular conditional statement. On line 2, we have to evaluate the condition of the while loop here, which is w is greater than or equal to x, and that is false, right? And then when the condition of a while loop is false, what do? You exit the loop itself.
Yeah.
Is there anything else to do in the then branch of the conditional statement? And when you're at the end of the then branch of a conditional statement, what do you do next? You get out, right? You just get to post right away and you're done. I always say, tell my students, like you guys, and there's no such thing as a dumb question, because when you're in a class, you have a question, something you don't quite understand, or I did not explain it well, then you can ask me, well, I don't really quite understand what you just said. But you know what? When I'm making questions, there are dumb questions, and this is one of those. It's not intentionally, it's not an accident. I actually intentionally made it simple so that you can get it done in a bit, and it will still test whether you understand the concepts or not. Okay, that really is the whole point, is do you understand the concepts? Okay, in the second one, we swap the values. So w and x will exchange the values for the starting point, and then we'll go ahead and trace this again, starting on line 1. W is less than X is false, and then where do we go? We go to the else branch, which is starting on line 6. Line 6 is evaluating another condition, which is the same thing. Okay, if it was false before, it has to be false at this point because I didn't have a chance to change anything. And when the condition of a while loop is false, you just get out of the loop. But when you get out of the loop, there's nothing else to do in the else branch, which means we will basically exit the whole thing, and you get the post, and that's the end of it. All right. So are there any questions about this one? It really is supposed to be that simple. All right, so that's the entire test. And we covered it in 31 minutes. It's always easier when we are looking at the answer. All right, so let me save it first. I'm going to save it to the tab folder, and then we can upload it. There we go. All right, so now the exam is over. We can talk about the topic that we were talking about before. All right.
How do we find out our scores for the
I have not finished grading yet. In fact, I'm still trying to set up, find out, what is the best way to set up for the grading, because I want to assign partial credit. We were talking about that, before this class started. How I like, only 2 types of answers: the ones that are completely missing, and the ones that are completely correct. It's like yes, full points. No, 0. But what about the ones that are partially right? Like, part of it seems to be right, and the other part is wrong. So I need to figure out a way to systematically assign points. And that has always been the most difficult part of grading exams like this. Multiple choice is easy, right? I mean, it's just, yes or no. Did you pick the right choice or not? But this is a little bit harder. It's very time consuming. I think, each test in the previous semester took about 5 to 6 hours to grade. Yep, for each exam. And I was only teaching 1 section of P300 last semester. This semester I'm teaching 2 sections. So let's go ahead and go back to where what we were talking about before the exam. Does anyone still remember vaguely what we were talking about?
Top-down design.
Yeah.
Top-down design, and we were using a particular example to illustrate it.
A map.
A map, okay, but I think we started on an
We were
algorithm.
using
We did factoring, very good. So we'll go ahead and do factoring again. So this time I'm going to start with something that's simple. Okay, let's start with 8. Okay, 8 is 2 times 4. 4 is 2 times 2. And 2 is 2 times 1. And by the time we get to 1, we can stop. Now, you have to look at this and say, this is 8. This is a prime factor of 8. That's how we get to 2. The 4 is really just the remaining portion of the composite number, which is basically 8 divided by 2. So that's how we read these lines here. And I'm going to cheat a little bit here and to pick the next example because it's not going to be as obvious. Okay, when you come up with examples to basically see how you do a certain thing, you don't want to always use simple cases like this because you have to kind of think about the difficult ones, like 391. Right. So 391 is what? See, you cannot eyeball this anymore. Well, I think most people cannot eyeball this. The only person that I can think of, who can eyeball this and say, "Oh, that's easy. I can find one prime factor right away." That would be Rain Man.
Is that 7?
Hmm?
Is that
Nope.
prime factor of 7?
Nope.
Last week you had it like where we could have, like for instance above it's like 2 by 4, and can we have like mismatched numbers or something like that?
Mismatch numbers?
Like never mind, that won't work.
Okay, how about this? Okay, how about this? Your job, as a supervisor, is to figure out, all the prime factors. Okay, so when it gets tough, what you do is you delegate, right? You say, hey, Joe over there, what is a prime factor of 391? You know, Joe is going to go through his calculator and go, okay, I'm trying to figure it out. 17. Okay. So what is your job? Now that you know 17 is a prime factor of 391. How do you figure out the rest? Well, that's just, 391 divided by 17, which turns out to be 23. Okay? Then the next step is just 23. Okay? So you ask Joe again because you just forgot all the prime numbers. So you ask Joe and say, hey Joe, I got a second question for you. What is a prime factor of 23? Now Joe being the person who knows the math and stuff like that says, well 23 is a prime number, so its only prime factor is 23 itself. Okay? So you say, okay, thank you. And the remaining portion is 1, and by the time you get to 1, you're done. All right? Now, but remember this example, okay? Remember Joe, because Joe is going to play an important role later on. And then obviously we have, other really, not so interesting cases like 101, which is just 101 times 1, and then we get to 1, we're done.
So I have a question. So was there a particular reason, because that's what I was talking about earlier, where you kind of had like mismatch numbers with the 17 and 23.
What do you mean by mismatch?
In other words, like I was thinking, like your goal was to, your algorithm was, keep splitting in half until you can't go no more. But in this particular case, is there another scenario that you could have chosen that were, maybe higher numbers than the 17 by 23 and then go down another level to that 17 by 23, or another algorithm that could have got to that same place?
Not understanding your question
In other words,
entirely.
numerically, could that have been done another way using different numbers?
Okay, the objective is to find all the prime factors. That's what we're trying to do. All right? So that's the objective of the algorithm. Your boss is telling you, give me all the prime factors of a particular number.
So how did you get to that?
How do I get to that?
Yeah.
That's how I do factoring.
I get that, but I'm saying, how did you come up with 17 by 23?
Because I don't want it to be simple. Because if it's simple, then you don't have to ask Joe. The whole point is I want you guys to think, hey, where's Joe when I need him?
So why not start with like factoring out 3? 3 is a prime number, so therefore.
Because it is obvious. Okay, when something is obvious, we don't think of top-down design anymore, because that task is just, oh, I know how to get to it. I know how to get to it. I know how to get to it. But when it's something like 391, it's no longer something that's simple, and most people just think, I wish there's some way to find the next, just a prime factor of the number, so I don't have to deal with it. Okay, and that's the whole point of top-down design, is to kind of delay the implementation of some of the logic of your code. So that's the whole point why I picked 391, because it's not obvious. You cannot just eyeball that. Okay, if you only pick examples where you can eyeball something, which means you just look at the number and you say, oh, it's divisible by 2, or it's divisible by 5, or 3, or something like that, then you cannot work on the algorithm in a top-down fashion, because it doesn't click, it doesn't trigger your mind to say, well, maybe I can defer this logic to another point. Okay, all right. So we'll just focus on these particular examples here, and then we'll start writing the code. I know we probably have started on this one already, but I'm going to start all over again because it has been a week and some people might have forgotten what we talked about last time. All right. So if you look at this process, okay, if you look at how I factor the 3 2's in 8, 391 and also 101, does it seem like the process itself is repetitive in a way? I'm doing something over and over again.
Yep.
Okay, very good. It's somewhat repetitive. And then if you figure out that, okay, it seems to be repetitive, does it seem to you that the number of times I have to go through the loop or the number of iterations I have to go through is fixed? Or do you think that kind of depends on the number itself? It depends on the number, right? Because I can give you 128. That will go through 7 times because 128 is 2 to the power of 7. Okay. If I give you a large prime number, it will only go through 1 iteration because it is a prime number itself. Okay. So whenever that requirement is met, that means you probably are looking at some kind of a loop. Okay. Now this is the part that is really hard to explain. How to write a program. Yep.
So,
How to get started.
like for instance, you gave an example of 128, or even let's just say 100, right? You can, obviously it's obvious, right? Those numbers, but you can. I guess what I'm trying to understand is the ruling. Like when you have, I could do 25 by 4 for 100, or
But
2
when
by
I ask,
50 or whatever.
hold on a second. I'm asking for prime factors, so you can only give me prime factors of a given number. So if you give me 100, and my job is to find a prime factor of 100, I can either give you a 2 or a 5, but I cannot give you a 10 or 25 or 4 because those are not prime numbers. Okay, and that's why you look at these numbers. I mean, 8 obviously has multiple ways to spell it out too, but I have to choose a way where it has one prime number and then the other one is just whatever is the rest of it.
Okay.
Okay. All right. So the first part is it is a loop of some kind. Does it seem like these are endless loops, or I have to perform an infinite number of iterations, or do I terminate at some point? I terminate at some point. And when do you think I terminate? The number that I'm supposed to factor is blah. 1. Very good. Okay, so we'll say this is a loop of some kind, but we are going to exit when, and I'll just spell it out in English. Okay, when the number to factor is 1. And that's it. That's my first iteration of this particular algorithm. Okay. So what I'm trying to do here is not to introduce any additional programming elements. Okay, we have all the constructs that we need already at this point. I'm trying to illustrate, the thinking process to create, to construct, to compose, to synthesize an algorithm to solve a particular problem. Okay, which is probably one of the hardest things to explain in this class. The pre and post conditions are basically logic and stuff like that. Yes, it is kind of tedious, and to a certain extent it's kind of difficult. But to me, to explain that is not as difficult as something like this, okay? Because I'm trying to explain a thinking process and not something that is technical, okay? Okay, so now that we have this, the next step I'm going to do is to use a variable, because every time when you look at the description of an algorithm, and it has something like this, okay, a phrase to describe a single thing, it means you probably want to replace that with a variable. Okay? So we'll just use a variable to replace that phrase, which is the number to factor. Okay, so we'll say let n be the number to factor, and that's all I'm going to do in this iteration of the construction of the algorithm. So all we're going to do is to say the number to factor is now replaced by a single variable called n. Okay, exit when n is 1. Is there a better way to express that using symbols instead of the word is? A single equal symbol in this class, and a double equal symbol in C, because in C a single equal is always assignment, a double equal is comparison. All right, so no big huge changes here. We're just using something to help us simplify and make the algorithm a little bit more concise. No big deal, but it is an important step. Okay, the importance of getting it to this stage already is actually very important. Do you think I start with 1 every single time? When my boss tells me, hey, Tack, give me all the prime factors of this number, do you think my boss is going to give me a problem to solve, like what are all the prime factors of 1? What are all the prime factors of 1, and so on? No. Probably not. So that means n is probably not starting with a value of 1. Does it make sense? Mm-hmm. Okay. So if n doesn't start with a value of 1, and yet I'm exiting the loop when n equals 1, and the loop doesn't seem to be infinite, what is that telling you? What do you think the loop is going to do? For sure. Or, okay, let me rephrase that question. I don't care how many iterations it will take, but at some point, n is going to become 1. Is that obvious? Okay. So that means loop until n equals 1. So we don't quite know which loop to use, whether pre-checking or post-checking yet, but we know it's a loop. But one thing is for sure, I know the loop is going to change n. Yep.
So that would mean that it's going to run at least once.
Not necessarily. We'll deal with that question later. Okay. That is one of the very last thing that we need to work on. Okay. But we know the loop is going to affect n somehow, because otherwise, n cannot move on. It cannot be changed to n. N cannot be changed to 1, and will never exit the loop. Okay. So that will be our focus. Is basically how are we changing n in each iteration? Because I know that n is getting changed, because otherwise it cannot get to 1. So now the question is, how are we changing n in each iteration? How are we changing n in each iteration? That is the question. And the question is really just coming from the code that we already have. It's coming from the exit condition itself, suggesting that n is going to be changed in each iteration. Is that okay? All right. Now, if the exit condition is not just n, but n equals y, or n is greater than m, or something like that, then you have possibilities. Because if you have multiple variables involved in the condition, then you can change one or the other, or both, in order to get out of the loop. In this case, it's pretty clear-cut, because we have one single variable in the condition. So that must be the variable that is getting changed in each iteration. All right. So now the focus is how are we changing n in each iteration. Let's go back to our examples here and see how n is getting changed. N starts with 8 in this case, then becomes 4, then becomes 2, then becomes 1. In this case, it starts with 391, then becomes 23, then becomes 1, and so on. So what do you think we are doing for each iteration?
Divided by a prime factor.
Dividing n by a prime factor. Very good. Okay, so let's just write it here. Okay, so we want to divide n by a prime factor of n. Okay. All right. So that's that's another iteration. That's really a good observation there. Okay. Next, we'll look at divide n by a prime factor, and we'll say, is this really a single step, or are there multiple steps involved in this case? There are multiple steps. The first one being finding a prime factor f of n. Okay. Now here's the part where Joe comes in very handy, or very important. Okay? Because if I only give you very simple cases like this one here, most people would just get stuck and go, okay, so what do we do now? I mean, not every number only has 2 as a prime number, so how do we get this done? But because we have the second example, where we say, it's kind of difficult to get to it, let's ask Joel, what is a prime factor of 391? Why don't we put that into the pseudocode as well? And I'll even refer to Joel here. Ask Joel for a prime factor f of n. So the prime factor that Joe is giving you, I'm calling it f here. Okay, so we can refer to it, in the rest of the program. Okay, and then what do we do with this number f? Maybe the first thing we'll do is to print it out, because after all, this program is supposed to give me a list of all the prime factors. Okay, so if I don't print it, then the algorithm can be completed and nothing is output to the end user. So I'll just go ahead and print it out. And then what do we do? Well, we still have to do that divide n by f, right? Okay. So if I say divide n by f, that really doesn't, I know what you meant when you said that, okay? But it's not clear whether we are just getting the quotient and do something else with the quotient, or what are we doing here? What do we do with the quotient of n divided by f? Sorry? Assign it back to n. Okay, so we want to update n with the quotient of n divided by f. So we have to make it clear, and one way to make that really clear is n gets n divided by f. Okay. So I'm breaking down a process into smaller chunks, but not really too small. Okay, in other words, I take this step here, which is really kind of descriptive of what we're doing with each step, into these 3 steps here, with only the first step being kind of, I'm not quite sure about that, but we'll just assume that we have something else that can find me a prime factor. Are we still doing okay so far with this logic? Yep.
So in that assumption, you're wrapping in the assumption that n divided by f is going to be a whole number?
Correct, because it is given to us that f is a prime factor of n, so that means f has to be, or n has to be wholly divisible by f. So it's because of how we find f that we know the quotient has to be a whole number.
Magic joke.
Yep. All right. So let's move on to the next, next stage here. And of course, when you're actually writing the pseudocode, maybe you should not refer to Joe. Maybe we should just say find a prime factor f of n. Okay, so that's an easy change. Okay. So we're almost done. The only thing that is remaining is, should we use a pre-checking loop or should we use a post-checking loop? Okay, because we have 2 types of loops, and those are the 2 that we can choose from. The difference is we have to use a post-checking loop if the condition or the variable or variables used in the condition is set by the body of the loop. Okay, before we can before we can perform the first comparison. If not, we can turn it into a pre-checking loop. Pre-checking loops are more general and they're more common in programming. So let me ask you this question. Does n start with any value before this algorithm starts? Yeah, my boss gives me a number, n, to factor. So n always starts with a particular number. It's not unknown. I don't have to wait until the first iteration to give n a reasonable or a meaningful value. So that tells me we can turn this into a pre-checking loop. Okay. So in the pre-checking loop, we have while something do and while, and then what we stick in between are exactly the same thing as what we had before. I left this one kind of blank because I want you to tell me what it is supposed to be, because we have already specified the exit condition. So what do we do with the stay in loop condition?
X does not equal, n does not equal 1.
N does not equal to 1. Okay. Now, we just have to be careful here, because if we say n does not equal to 1, that means n can be less than 1, and it can be greater than 1. So in that case, you really have to ask the question, if this is a homework assignment for, let's say, cisp300, and the instructor doesn't tell you anything else about n, it is your job to ask the instructor, can I assume n to be non-negative? Okay? Because if you cannot assume n to be non-negative, then you have to ask, okay, if n is negative, do we want to print out the factors and then say multiply by -1, or how are we going to solve that problem? Okay, if your instructor comes back and say n is always greater than 1 or greater than or equal to 1, then you can just say, oops, this. Okay, so that part depends a lot on the assumptions. Okay, assumptions on the variable n or the initial value of n. Am I making the point across? Okay. So you do have to kind of think about all the different cases. If the instruction of your homework assignment is not clear, you have to ask your professor and say, well, it's not quite clear whether we have any type of constraints on n. Can I make assumptions? Yep.
Are you creating a loop for each block? I mean, if you are one, like what? Are you creating a loop for each function, like each command?
At this point, we don't have the notion of a function or a subroutine yet. So by the time we get to subroutine, yes, find a prime factor f of n will turn into a subroutine. But at this point, we don't use the word subroutine. We just say, okay, we're deferring that to another algorithm. Okay. That's a good question. All right, so we're done with this one here. Are there any questions about the process of synthesizing or creating the algorithm itself? No questions? It took me a long time to really, come up with a way to explain, how to write an algorithm, step by step, because that really is one of the hardest things to explain is, how do you come up with an algorithm? Before I started teaching, it just, the loop just pops up in my mind. Okay, that's the best way to describe it. It's just, okay, I sit down and I just start typing, and then it just comes to me. But as I start to analyze, I can come up with these steps here to analyze the problem, and also step by step figure out how are we going to solve the problem. All right. But we are not entirely done yet, because Joe comes back to you and say, we are not done. What if I'm not around? Right? What if Joe is not around? If Joe is not around, then nobody's going to do that step. So now you have to figure out how to do that step in case Joe is not around, right? So that becomes our new problem, which is a smaller sub-problem of the original one. Okay, so now we have a new algorithm to write to find a prime factor f given n. Okay. How are we going to do this? Well, instead of just sitting down staring at the question itself, the best way to do it or to get started is to give yourself examples to try out by hand. Okay? Because if you cannot do it by hand, there's no way you can write an algorithm to describe the process. So you've got to do it a few times by hand and use non-trivial examples along with trivial ones. So we'll start with trivial ones. Okay? So let's say n is, I don't know, 16. Okay, what is a prime factor of 16? F is 2. Okay, what went through your mind when you came up with that answer? I don't know. It's just obvious to me, right?
Well, I started with the square root, which was 4, which was divisible by 2, so I just kept
But
going down.
how do you know 16 is a square itself?
Well, it's because I learned it a long time ago.
Exactly, it's because we learned that a long time ago. Okay, so that doesn't really describe how to describe it logically, because the computer has not learned anything, right? Yep, go ahead.
Basically, your eyeball, it's divisible by starting with the smallest number you can figure out.
Okay, well that's a good process. So maybe we should start with something that is not so simple, right? N equals to 391. Okay. Now, with 393, n equals to 391, most of you would say, oh, f equals to 17 because text said so earlier in class, right? Okay, so maybe that was not a very good example. So let me cheat again and figure out something that is not easy to figure out. Okay, so we'll pick something that's kind of nasty here. That's a good one. I like this. I like it because it's also kind of like there's a symmetry to the whole thing too. Okay, n equals 8,989. Okay, so now how do you figure out a prime factor of 8,989?
Google.
Okay.
Well, I found a prime number website and just popped in the number, so it told me. It said 89 by 101.
Okay, so if you can Google for the answer, so can your boss. Why is he hiring you? Or why is she hiring you? Okay, yep.
Maybe he wants to manage like 100 people who can Google, and he can't Google for 100 people.
Yep. If Google is the answer, then we don't need employees anymore, do we? Okay. And there might come a time when Watson, not Google, will get to that stage. Does anyone know what is Watson? Who is Watson?
An AI type deal.
Yes, it's the AI that played Jeopardy. But they have already started to actually make a commercial version of Watson for, I think, medical diagnosis. So you can basically describe the symptoms, and other things, and then Watson can, try to figure out, what is causing that, which I think is really cool.
It's cool, and it's also really bad because sometimes there's circumstances that if they're not perfectly described, you're gonna run into a real mess of medical practice.
That is true, but
Because if it misinterprets something, and can't actually visually take in the symptoms,
Mhm.
then there's that element there that says, a doctor could see it and be like, oh, well, yeah, you described this, but I also see this. So I know that I can't prescribe you this and this, but I can prescribe you this or this.
I'll put it this way, based on how Watson can beat the Jeopardy champions, I think Watson will be more reliable than maybe 70% of the actual human medical doctors out there.
Just saying.
Well, I mean, we are really getting to the point where computers or programs or AI, can in a very narrow field outperform humans. I mean, beating a chess champion has been done many times already. I mean, it's not a fun thing anymore. Making a person play against the computer in chess is no longer a fun thing because the computer always wins. Yeah, that was considered AI at one point of time. It's no longer considered AI. It's just mechanical now. Anything that is done reliably is no longer AI. AI is basically what is at the verge of being possible and to be able to be done by computers. That's really the AI field. So it's always changing. It's always the next thing that can be done by computers.
So Google car is not going to be considered AI in like 30, 50 years or something.
Give it 20. Okay? 20 years later, and many of you will still be around. Ask a young person who's going to a car lot and say, well, would you consider this car that can drive itself, artificially intelligent? Then that person will come back and ask you and say, do you consider your toaster intelligent? Because it's going to be like that. I mean, once it can be done reliably and we know it mechanically how to do it, it's just an appliance. It's no longer intelligence. Yep. All right, so we're back to 8989. All right. So unless you Google for 8989, you probably won't know the answer. So how do you do it step by step?
You start dividing by numbers or whole numbers until you got something that was only divisible by one in itself.
Exactly. So you try out different numbers. So would you try something like this, 8989? I'll just randomly pick some number here and say, let's try 23. And if that doesn't work out, I'll try maybe 31. Or do you guys have a more systematic way to do it?
Yeah, just do it completely sequentially.
In the sorted order, right? You try the smaller numbers first, and then you move on to the larger number because it really doesn't matter. I mean, because your boss is really just asking you what is a prime factor of 8989, and your boss didn't say you have to do it within a certain amount of time. Yep.
So it's kind of like creating. So for instance, this can be any number. So in this situation where it's 8989, you start with the lowest prime factor and you keep on going up until you find the number that it can pretty much be multiplied by to reach this number.
Until you find a factor, until you find the first prime factor. Okay?
So
but how do I identify a prime factor? In other words, if I divide 89 by 31, what do I get? I get a quotient with a remainder, right? In this case, since 31 is not a prime factor of 89, what do you know for sure about the remainder? The remainder is going to be greater than 0. Well, it's positive, right? So we know that, okay? So a prime factor or any factor has the special property of when you divide the number by a factor, the remaining or the remainder of the division is 0. That's how we can tell whether something is a prime number or not. I mean a factor or not, okay? So I'm gonna cheat a little bit here and use a spreadsheet to help myself to do this. Okay, so I'm gonna start the new spreadsheet. Right, okay? But what I'll do is something that seems to be kind of not so smart, okay? So I'll do this here. 89 is the number I'm trying to figure out. So what I'll do is I'm gonna say refer to $1. So I can just repeat this whole row here. It'll be clear why I use a spreadsheet to do this. The first prime number is what? What is the smallest prime number?
2.
1. Oh, 1, I guess.
1.
By definition, 1 is not a prime number.
Okay.
2.
2. All right, very good. All right, so 2 is the least prime number. And then you guys will say, Tech, why do you bother? 89 doesn't end with 2, 4, 6, 8, or 0, so it's not divisible by 2 for sure.
So the program will work on all kinds of numbers, right?
Exactly, so we want to make an approach so it's generalized, okay? So we'll start with 2. Is it wrong for me to start with 2? If I start with 2, is it possible that I misidentify 2 is a prime factor? No, it's just wasting time because it's obvious to us, but it will still give me the right answer and say, nah, 2 is not a prime factor of this particular number. Okay, so but how do I know? Well, the way I know is because I can do a mod operation. A mod operation is really a division, except we don't get a quotient, we get a remainder back. Okay, so it's the remainder of a division. So in this case, we specify this number to be our dividend, the number being divided, and this number to be our divisor, which is the number that is dividing the other one. Okay, and the remainder is 1. 1 does not equal 0, so 2 is not a factor of 89. Is that okay so far? Okay, so I can even use another column to indicate the answer here. I can say if this number does not equal to 0, then I want to specify a string and say not factor, otherwise we say factor, like that. Yes, you can use conditional statements inside a spreadsheet as a formula. And you can even nest them too.
It's gonna be a pain in the butt though.
Huh?
It gets to be a pain in the butt.
Yeah,
after
because
the
you have to
second
fit
level.
everything on a single line, yes. Okay, so if that's not working out, we can try something else, okay? So this is the really cool part here, because I can now refer to this as the previous number plus 1. And this one, I can just refer to the previous number. I can just drag this one down like that. And this is really just the entire, these two I can just drag down or just duplicate from the one before. So now, if you look at the equation on this particular cell, I am dividing 89 by 3 and end up with a remainder of 1 again. So I know 3 is not a factor of 89. Are we doing okay so far? So why do we waste this much time on something like that? Well, so I can do this. Oh, I forgot this column. Always miss something. I don't think I have found it yet. Yep, there's a factor here, there's another factor there. Okay, but that doesn't seem very smart. I mean, why do we even try 4? We tried 2 already, and 4 is a composite number with 2. It cannot possibly be the answer. Well, let me ask the same question that I asked a little bit earlier. If I try 4, is it possible that I misidentify 4 as a prime factor of 89? No, because the remainder is going to be non-zero, so it won't be considered as a factor anyway. So the fact that it is non-prime doesn't even matter. Is that making any sense? Okay, because to most of you, it seems like maybe we should only try prime numbers, right? But if you only want to try prime numbers, you need to find a way to find and store all the prime numbers. It's a lot easier to just go for the next number. Okay? efficiency is not important in this case. Okay, we're just focusing on an algorithm that is correct. Okay, focus on correctness first before you focus on efficiency. Okay, are we still doing okay so far? Okay, so you look down this list here. You know, you can look at column E, and we have not factor, blah 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 blah. Okay, we find one. So 89 is a prime number, a prime factor of 89. That is cool. That's actually kind of obvious, right? You look at the number 89, doesn't it kind of scream to you that 89 itself is a factor of that number? Yep. Okay, so once we identify that number, we divide 89 by 89. Well, in this case, I don't even need to do that, right? Because remember, the algorithm that we want to specify now is just to find a prime factor f given n. So once we get to 89, we are done. Okay? Are we okay with the process of finding a prime factor given a particular number? Okay? May not be the most efficient way to do it, but it is correct. Okay? It always finds the right answer. Okay. Next, we want to write the algorithm to do just that. If you look at something like this, it doesn't tell you the structure of the code. It doesn't tell you the structure of the process itself. On the other hand, if you look at something like this, I think it more than sufficiently illustrates the structure of the process, right? That is why, when you want to write an algorithm, you don't want to start with trivial cases. You want to start with challenging cases where eyeballing it doesn't solve the problem. Okay, you actually have to force yourself to use a structured method to solve the problem. Okay, so given this kind of structure, we can go ahead and start to write the algorithm, just like before. Okay, so just like with the other algorithm, we'll start with this one. And the first question is, do you think it involves repetition? Okay, let's switch back to the spreadsheet and see if repetition is present. I think there's a little bit of repetition here. Okay, all right, fine. We say loop and loop. And when do we exit in this case? Let's take a look. Okay, we are not exiting, not exiting, not exiting, not exiting. Okay, we got the answer. We can get out. How would you describe this particular step? Why are we exiting? The remainder of the division is 0. Very good. Okay, so we can go ahead and just write that too. So end loop exit when the remainder is 0. I know this is awfully vague, but that's okay. Okay, it's just the first step. Okay, so after the first step, once you identify this is a loop and we have some kind of remainder to deal with, then you have to be more clear. The remainder of what divided by what. Okay, that's what you need to specify. Okay. All right. Maybe the remainder of n is given to us, so it's definitely here. Divided by a potential factor. Okay. Fine. All right. And we'll call this another revision. And you can see I'm not going to start the actual algorithm and do it step by step, line by line, because that's not how we think. Okay, can we clarify this a little bit? If you look at a potential factor, doesn't it sound like it's a phrase to describe something that you use in the algorithm? Maybe we should name it with something. Okay, maybe we should name it f. Okay, for factor. Okay. So in this case, we'll go ahead and say let f be a potential factor of n. Okay. Well, that makes it a little bit easier because I can now replace this entire phrase with f. The remainder of n divided by f is 0. Well, maybe we can now use the mod operation to kind of explain this a little bit better. So the next revision. Would basically say the same thing, except it is just expressed a little bit more clearly. It will say n mod f equals to 0. So this is a new operator, n mod f. Mod is just like divide, except it gives you the remainder of the division instead of the quotient of the division. Are we doing okay so far? Does everybody understand the 4 terms related to division? Yes? Okay. Okay, I'll just double check and make sure. How do we call this part here? The dividend. Okay. So we have dividend here. How do we call this term here? Divisor. And this part here? Quotient. And this part here is our remainder. So a mod operation needs you to specify what is the dividend, what is the divisor, and it gives you the remainder without the quotient. The remainder is the only thing it gives you. Okay? All right. Cool. Now, this is also a very important step here because if the exit condition looks like this, and we think this loop is not infinite, okay? Because every number has at least one factor. Even prime numbers has a factor, which is itself. So it has to get out at some point. So in order to get out of the loop here, we have 2 variables in this case. To make this condition true, I can change one, I can change n, I can change f, or I can change both of them to eventually make this condition true. So now the question is, can I change n? In other words, my boss tells me, hey, give me a prime factor of 89, and I just say 2. Because guess what? I just changed the problem. I thought you asked me what is the prime factor of 2. It is 2. Can I change the question itself? No.
Well, what if you assign n a random value in the beginning?
N is given to you.
Oh, n's. Okay.
N is given to you already. Okay, so I cannot change n. So without changing n, what is the only way to get us out of this loop? There's only one other variable, which is f. Okay, so I know this loop is going to do something to f. Okay, now this is a very important step because by analyzing the exit condition, it gives you a clue of what you have to do in the loop itself. Okay, what is being changed in the loop to eventually get us out of the loop. That's good. And we have 2.5 minutes. All right. So we refer back to our example here. Which column do you think represents f?
D.
Column C represents f. Column D represents n mod f. Okay. Can you see a pattern to column C? Just always plus adding 1 to the previous one. Okay. Well, maybe we can do that too over here by saying f gets f plus 1. I mean, would that work? Yeah, I think that would work. Okay. The last question we have to answer is, there are 2 more questions actually. The first question is this a pre-checking loop or post-checking loop? And then the second question is, hey, f has to start somewhere, and I haven't even specified, how we start with f. Now those 2 questions are related because the first one is, we can say f starts with a value of 2, but if f starts with a value of 2, you have to use a pre-checking loop because otherwise f would become 3 before you check it. Okay, so in this case, the solution is while n mod f. Okay, how do we relate n mod f to 0 to stay in the loop?
R is greater than 0. Or does not equal 0.
Rated not equal to 0. Okay, so not equal to 0 is the more general way to say it. Okay, and inside we still have f gets f plus 1, and while here, that's one way to do it. The other way to do it is to say f gets a value of 1 to begin with, but we will use a repeat until or post-checking loop here, which means we have to go through at least 1 iteration. So by the time we get to the until, f is going to be at least 2 in this case. And we want to say until n mod f equals to 0 because this is specifying an exit condition. When the condition is true, we get out of the loop. Okay, here is my last question, for the last 15 seconds. Which one is better? They are truly equivalent, okay? There's no difference whatsoever in terms of correctness or what cases they can handle, but which one is better? Say again? Sorry?
The repeat one, the second
The
one.
repeat one?
Yeah.
Why do you think that?
It just looks kind of neater to me.
Okay. I would use the first one because the first one is clear what is the first f that I would use in the condition. Whereas in the second one, it is not clear because the initialization is only initializing f to 1. But I have to go through the loop to see what the loop is doing to f in order to figure out what is the actual first value of f that I'm actually testing. So that is not as direct, and that's why, personally I prefer the first one. But if you implement it using the second loop, it's going to be, correct as well. It's just that if it doesn't work, it's not as clear why it's not clear. All right. Thursday, and there's no homework at this point, because I'm busy grading.
We have the